In this set of notes, we're going to begin looking at the idea of estimation. So our overarching goal here is we want to be able to make inference about unknown population parameters. So some examples. So we might want to estimate the proportion P of Americans who approve of the job President Trump is doing. And so notice the only way to directly calculate P would be if we spoke to all Americans, and we'll limit that to adult Americans, but still, we would have to talk to all of them and find out if they approved. So notice, calculating P directly is not really possible. We might want to estimate the monthly budget mu of a family living below the poverty line, and again here we'd have to interview all families living below the poverty line in order to directly calculate mu. Again, not something that's feasible. Or estimate the standard deviation sigma of a patient's weight loss after bariatric surgery. So again, in all three of these scenarios, calculating these values directly would be very difficult. So we're often going to call the parameter of interest the target parameter, and we're often going to have other nuisance parameters. So for example, when we estimate mu, sigma squared would be considered a nuisance parameter. So there are two primary types of, or really two different types of estimates, and you've probably seen both of these before. There's what we call a point estimate, so that's a single value estimate. So for example, we might say that P hat is equal to 0.8, that is 80% of all adult Americans not working from home report wearing a mask in the workplace. And so here we're making a distinction. P hat is not equal to P, but we're using P hat as a way to estimate the true value of P. Another example could be what's known as an interval estimate, and here we would say between 67 and 93% of all adult Americans not working from home report wearing a mask in the workplace. So notice here the estimate is an interval, and then we could talk about the probability of that interval covering that fixed parameter that we don't know the exact value of. So we've got some definitions here. An estimator is a rule or a formula that tells us how to calculate the value of an estimate based on the measurements contained in a sample. And there is a difference between an estimator and an estimate. An estimator is a random variable. We have an estimator before we plug in all the values of our measurements, and the estimate is the number that we find. So this is what we find after we perform calculations. We have an estimate. So for example, one estimator of mu is the sample mean. If the population is symmetric, another estimator of mu is the sample median. And so the question here is, which one is better? So you can imagine kind of in a picture here. Here's an example of a distribution that is symmetric. So notice that we know that both the mean and the median are in the middle. So, oops, I spelled median wrong there. So if they both occur at the middle, which one is the better estimate? And the answer is we want the one that has the less variability. And so what we're going to talk about now are different ways that we could evaluate estimators. In particular, we're going to look at what is called the bias and the mean squared error. So think of firing a gun at a target. So you've got your target here, and we'll say the bullseye is in the center. So the parameter that we want is going to be in the center. So it is possible to fire a single shot and hit the bullseye. In other words, this would be the same thing as we select one random sample, and it ends up that that statistic that we find from that sample estimates that parameter correctly. But it's more likely that that single shot is going to miss. It's not going to hit dead on. So we can't reliably make any conclusions based on a single shot. However, if someone were to fire 100 shots and hits the bullseye every time, we would be impressed. And so the idea is if we draw 100 random samples and hit the bullseye every time, we would conclude that we had a good estimator. And so notice here we're deciding if an estimator is good based on using the procedure many, many times. In other words, we look at the sampling distribution of the estimator. In general, we're going to denote the parameter by theta and the estimator by theta hat. And so the reason we're doing this is this way it's generic enough whether we're talking about mu or p or sigma. We're just going to use theta as this generic way to denote the parameter of interest. And so the question is, what qualities would we like theta hat to have? And what we would like is we would like on average theta hat to be equal to theta. So in other words, what we're saying here is we would like the expected value of theta hat to be equal to theta. And that's going to bring us to our next definition. Let theta hat be a point estimator of the parameter theta. We say that theta hat is an unbiased estimator of theta if the expected value of theta hat is equal to theta. Otherwise, theta hat is biased. So let's look at a picture here. So let's visualize what the sampling distribution of theta hat might look like. So one potential sampling distribution we could have would look like this. And let's suppose that theta occurs right in the center. So in other words, the expected value of theta hat is equal to theta. So in this case, we would say that theta hat is unbiased. On the other hand, if we drew the sampling distribution of theta hat, and let's suppose that theta occurs here, and we know for this picture the expected value of theta hat would occur at the center, here we have that the expected value of theta hat is greater than theta, so therefore here we would say that it is biased. So the bias B of a point estimator theta hat is the difference between the expected value of theta hat and theta. So suppose we have two unbiased estimators of theta, theta hat 1 and theta hat 2, with the following sampling distributions. So let's say that for theta hat 1, we have the following. And we know that theta hat 1 is unbiased, so we have theta in the center, versus the sampling distribution for theta hat 2, which is again unbiased. But notice that theta hat 2 has a much larger variability. So in this case, we would say that theta hat 1 is the better estimator because it has a smaller variance. So if theta hat 1 and theta hat 2 are unbiased estimators of theta, then theta hat 1 is a better estimator if it has smaller variability. And we say that theta hat 1 is more efficient than theta hat 2. So how do we compare the biased estimators to unbiased estimators? Well, recall the following. So here we have the definition of the variance of theta hat. So if theta hat 1 is an unbiased estimator, we know that the expected value of theta hat 1 is equal to theta. And what we really want to do is determine how close theta hat is to theta, not how close theta hat is to the expected value of theta hat. So we define here what we call the mean squared error. So the mean squared error is going to be equal to the expected value of theta hat minus the expected value of theta hat squared. Oh, and I just realized there is a typo here, so let me fix this. I'm actually going to fix this in your notes because that's incorrect. This should say the expected value of theta hat minus theta squared. Now that makes more sense, otherwise we would have just had the variance again. So our goal is to find an estimator which minimizes the MSE. And so here is a useful fact. The MSE of theta hat is equal to the variance of theta hat plus B squared, or the bias squared. So let's look at an example. Suppose that we have y1 through yn, our IID gamma, alpha, with beta equal to 3. So the first question is, y bar an unbiased estimator of alpha? So we know from previously the expected value of y bar is equal to mu. And now since we are working with a gamma distribution, we know that mu is equal to alpha times beta. And we're given that beta is equal to 3, so this is going to be equal to 3 alpha. And notice that this is not equal to alpha, so therefore y bar is not an unbiased estimator. So let's find the MSE of y bar. So the MSE of y bar is going to be equal to the variance of y bar plus the bias squared. So we're using that fact from the previous page. So we know that the bias is equal to the expected value of y bar minus alpha, which in this case is going to be 3 alpha minus alpha, which is equal to 2 alpha. And then also recall that the variance of y bar is equal to sigma squared divided by n. Well, since we are working with the gamma distribution, sigma squared is equal to alpha times beta squared. And we divide that by n. And remember that that beta is equal to 3, so we have 9 alpha divided by n. So therefore, the MSE of y bar is equal to 9 alpha divided by n plus 2, and that's 2 times alpha squared, which is equal to 9 alpha over n plus 4 alpha squared. So next, can we modify y bar to get an unbiased estimator of alpha? Well, since the expected value of y bar is equal to 3 alpha, we can use alpha hat as our estimator, where alpha hat is equal to y bar divided by 3. So let's find the expected value of alpha hat and confirm that it's equal to alpha. Well, the expected value of alpha hat is equal to the expected value of y bar divided by 3, which is equal to 1/3 times the expected value of y bar. And we've already shown that that expected value is equal to 3 times alpha, so this is indeed alpha. So alpha hat, which is equal to y bar divided by 3, is an unbiased estimator of alpha. Okay. So let's find the MSE of the unbiased estimator that we just found. So notice, since it is unbiased, our bias is going to be equal to 0. So now we just need to find the MSE of y bar divided by 3. Well, again, since the bias is equal to 0, this is going to be the same thing as the variance of y bar divided by 3, which is equal to 1/9 times the variance of y bar. So based on what we have earlier, this is equal to 1/9 times 9 alpha divided by n, which is equal to alpha divided by n. So notice here that alpha divided by n is less than the MSE of y bar, which we found up above. So we have an estimator which is unbiased and also has a smaller MSE than our original estimator. So our goal is to get unbiased estimators with relatively small variances. In other words, we want to minimize the MSE. So let's look at some common point estimators. So these are ones that you have probably seen before. So here we have our parameters. And here we have the common point estimators used to estimate those parameters here in this column. And the next one, we have the expected value. So first, notice that these are all unbiased. So if we want to estimate mu and we use y bar, we see the expected value of y bar is equal to mu. Now finally, in the last column, we have the standard deviation of these, and so I'm going to write these in. When we work with y bar, we know that the standard deviation is equal to sigma divided by the square root of n. So we've seen that before. When we want to estimate the population parameter p, we know that we can use p hat, and so you've probably seen this formula before. We have p times q divided by n and the square root of all of that. When we are interested in the difference of means, mu1 and mu2, here I'm going to have the variance from the first population divided by its sample size plus the variance of the second population divided by its sample size and then the square root of the whole thing. And so you've probably seen that formula before. Now one thing here is we do have to assume that those two samples are independent from one another. And then something very similar if we look at the difference in proportions. We have p1 times q1 divided by n plus p2 times q2 divided by n and the square root. And since the spacing here is pretty small, I'm going to add these in to the PDF that you have. Alright, so our next question we have here is how large do sample sizes need to be? And so here we have a couple rules of thumb. You've probably seen these in your intro stat course. Later on, for your first mini project, you're going to see what I'm going to have you do is actually verify, is n greater than 30 always large enough? And what you're going to find out is depending on the shape of the population, it might not be. So although unbiasedness is a good quality for an estimator to have, not all estimators are unbiased. However, do note that y bar is always an unbiased estimator of mu. And so this can be very helpful in guessing what an unbiased estimator might be. So recall that the sample variance has n minus 1 in its denominator. Why is that? Why wouldn't dividing by n make more sense? Well, it ends up that the reason for this is that if you divide by 1 over n, you get a biased estimator. And I'm not going to show it here, but if you divide by n minus 1, you end up with an estimator that's actually unbiased. So that's why you see that in the sample variance. Alright, so the last thing we're going to talk about here is evaluating the goodness of a point estimator. So we call the error of estimation epsilon is the distance between an estimator and its target parameter. So that is the following. So notice here we have the absolute value of theta hat minus theta. And so notice that epsilon is a random variable since theta hat is random. And so ideally we would like epsilon to be small. So if we let b greater than 0 be any small number, so notice this has nothing to do with the biased b, what we're looking for is we would like the probability that epsilon is less than b to be equal to the probability that the absolute value of theta hat minus theta is less than b. We would like that to be some large number, and since this is a probability, a large number means that it's close to 1. So we have the following. So the probability that epsilon is less than b is equal to the probability that the absolute value of theta hat minus theta is less than b, which is equal to the probability that theta hat minus theta is between negative b and b. And here we're going to get theta hat by itself, since that is the random portion, and so notice that's equal to the following. So in other words, we have this picture right here. And so notice this deals with the sampling distribution because theta hat is our random piece, so we're looking at the distribution of that estimator. So we want to work problems where we specify values of the probability of epsilon less than b is equal to the following and solve the equation for b. And so if we know that sampling distribution, we get the following. And then suppose we didn't know the sampling distribution, then Chebyshev's theorem tells us this piece right here. So it ends up that 2 times the standard error, or 2 times the standard deviation of theta hat, is a good approximation of the bound of error of estimation. And so you should notice this is kind of leading towards that idea of confidence intervals that you've seen previously in your courses, specifically probably your intro statistics course, and eventually we're going to use this idea to lead into the idea of confidence intervals. Alright, so let's look at an example and put this to use. A recent study investigated the effects of Buckle Up Your Toddlers campaign to get parents to use the grocery cart seatbelts. Investigators observed a simple random sample of parents in a large city and found 192 out of 594 parents buckling up their toddlers. Estimate P, the fraction of all parents of toddlers that buckle up their toddlers, and using the grocery cart seatbelts, and place a 2 error bound on the error of estimation. So here notice that we have n is equal to 594, and we're interested in the parameter p. So in this case we're going to use the estimator p hat, which gives us the estimate 192 divided by 594. So if we wanted to place a 2 standard error bound, we would have 2 times the standard deviation of p hat, which is equal to the following. So here is our question, is what does p times 1 minus p look like? So let's draw a plot here. Well, we know that p is restrictive between 0 and 1. So when p is equal to 0, we know that p times 1 minus p is equal to 0. Notice that when p is equal to 1, that p times 1 minus p is also equal to 0. When we have a half, on the y-axis we would have a half times a half, which is 1/4. So we get something that looks like the following. So if we have to estimate p to get the 2 standard error bound, one option is to use p equals a half, because notice at p equals a half we've maximized p times 1 minus p, so in other words you're maximizing that variability. So here if we have 2 times sigma p hat less than or equal to 2 times 1/2 times 1 minus 1/2 divided by n, well this is going to be 2 times a half times the square root of 1 over n, which is equal to 1 over the square root of n. And remember here we had n was equal to 594. And so here we would find our error bound is equal to 0.04. And this would be the most conservative way to estimate this, again, based on the plot that we have above. Now another option is we could have used p hat our estimator for p. So in this case, we found that our estimate was 192 divided by 594, so we could set p hat equal to that, and then plug that into 2 times the standard deviation for p hat to get that estimate. And if you do that, So option 2, we could find our error bound using p hat. If you plug that in, you'll find this is equal to 0.038. So notice we do actually get something that is slightly less, because again, that 0.04, that is the most conservative value that we could have. Suppose that we want to compare the performance of freshmen and sophomores on an aptitude test. A random sample of 32 freshmen had an average score of 540 points and a variance of 2,500. An independent random sample of 50 sophomores had an average score of 600 and a variance of 2,890. So first we're going to estimate the difference in mean aptitude scores for the freshmen and the sophomores. Before we do that, let's summarize our sample information. So for our first group, we had a sample size of 32, we had a sample mean of 540, and we had a sample variance equal to 2,500. For our second group, we had a sample size of 50, we had a sample mean of 600, and we had a sample variance equal to 2,809. Alright, so if we wanted to estimate the difference in mean, what we would do is we'd take Ybar 1 minus Ybar 2 equal to negative 60. So then we could place a 2 standard deviation bound on the error of estimation. So notice here that sigma of Ybar 1 minus Ybar 2 is equal to the square root of sigma squared 1 divided by n1 plus sigma squared 2 divided by n2. So one way that we could do this is we could estimate using our 2 sample variances. And so this would give us the following. So what this tells us is we estimate the difference in mean aptitude test scores for freshmen and sophomores to be negative 60 points. And further, we expect that our error of estimation to be less than 23.178 points, with approximate probability 0.95. So that approximate probability of 0.95, remember, that's where that 2 is coming from, and that's assuming that normality and applying the empirical rule. So we can convert this to an interval, and so if we converted it to an interval, we would have the following. We would have negative 60 plus or minus the 23.1780. So really what we've done here is construct a confidence interval. And so what we say here is we are 95% confident that freshmen have a mean aptitude test score that is between 36.822 and 83.1780, lower than that of the mean aptitude test scores of sophomores. Now, this is as far as we're going to go for confidence intervals right now, because again, here in a couple weeks, we're going to pick confidence intervals back up. So, keep this idea here of having your point estimate and then estimating your error in that estimate kind of in the back of your mind, because we're going to pick this idea back up here in a couple weeks.